Okay, well, thank you for being here today for the third lecture in this year's season of geology talks, and the third one that has Siletzia as a component. First, I'd like to give thanks to the peoples of the First Nations who were great stewards of the land, that the lands that we call the Salish Sea and where we call Port Townsend home. I have some announcements. The first announcement I would like to provide is, we have had a lot of speakers to QGS from all walks of life. Some that are celebrities like Nick Zentner. And since we're in a church today, I would like us to put the Zentner family in our prayers and our thoughts. Nick's wife had emergency surgery yesterday and will be in Harborview Hospital for the next couple of weeks. So please have him in your thoughts and prayers. The next talk is on January 11th, 2025, and that's Paul Bierman. He will be using the past to look into a warming future by talking about climate science, environmental history, and stories related to people who studied Greenland. And these stories can also be found in a book that he has recently released called When the Ice is Gone. The 2025 lineup of lectures is developing beautifully, and check our website frequently for updates on the dates and talks, titles of the talks. A few of the geologists tonight will be joining Megan down at the poorhouse right after the talk. And then tomorrow we also have a meet your local geologists from 3 until 5. So bring your favorite rock that you want to talk about or a geologic process that you have a question about. And we would be happy to see you. The Quimper Geological Society, QGS, has been around since the early 2000s. That began in Kitty Reed's living room. It has been a social event for the community of Port Townsend, and since the early 2000s, or since 2011. We have had the fortunate ability to have many of our friends from the Washington Geological Survey present to us, and some of them even are gracious enough to come back. So they like to share their projects that they're currently working on and help us understand what the risks are for being citizens of Washington State. So it is with great happiness that I get to introduce one of the state's geophysicists, Megan Anderson. She has a degree from Carleton University in geology, her PhD in geosciences from the University of Arizona. She taught 10 years at Colorado College, had tenure, and jumped at the chance to come back to Washington State when the job for the Geological Survey opened up, and was right down her avenue. So she moved back to Washington in June of 2018, and we had the fortunate ability to have her here in November of 2018. Megan knew from an early age that she wanted to have geology as one of her passions. Mount St. Helens was, when Mount St. Helens exploded, she was only 7 years old, and her parents, who were into natural sciences, took Megan to the mountain for the first time. And when I asked Megan when did she know she would be a geologist, she said her freshman year of college she took a geology class and knew this is it. Many of us have that. And so then I asked her about what was her favorite part of teaching or her favorite projects that she's worked on. In teaching, Megan loved the mentoring capacity, her one-on-one labs, and working with students on research. In regards to her work that she does now, she's still a teacher. She's training people all over the states on how to use the geophysical equipment that she as well had to learn by hands-on. Right now, all of the projects she is working on are her favorites, and especially the mapping the faults of Seattle and Tacoma. So please provide a warm welcome back to Megan Anderson. Thank you, Megan.
All right. Thank you so much for having me back. Clearly, I didn't bore the pants off you last time, so you want to hear more. I'm really excited to be here today to talk about a project that I started actually during my postdoc back in the mid-2000s. As Carol mentioned, I went off and did a lot of teaching after grad school. And I worked on this very slowly over the course of time. And finally, once I got here, was able to kind of push it through and get it published. And so it came out this last year in the journal Tectonic. And I want to tell you this story because I think it's just such a cool and interesting story where the data can take us to places that we can't even understand from looking at the rocks on the surface. And so I hope I can make the geophysics understandable to you. And if you have any questions after the talk, I'm happy to answer them because we're not gonna be shy about diving into some geophysics here. So this is a picture from Mount Erie from when I was still teaching. My co-teacher Eric Leonard, he's a glaciologist, and we're up there on looking out over the Puget Lowland and admiring how you have the glacial striae on Mount Erie, and you can look out over the lowland from there. You know the ice was at least as high as that mountain. And so it would have filled the whole valley in front of you. So it's a really spectacular view of thinking about what it was like a few tens of thousands of years ago during the age of the glaciers filling up the Puget Lowland. Well, I'm going to talk to you today about that same kind of view of what the Puget Lowland would have looked like a few tens of millions of years ago. So yet another order of magnitude back in time. And I think it's a fascinating story, and I hope to bring you along with me through it. I want to thank my collaborators on this paper, my postdoc advisor, Rick Blakely, ex-geologist from Washington Geological Survey, Joe Dragovich, without whose help I would not have no rocks to tie to the geophysics. And I tell people that without geology, geophysics is just physics. So you'd be stuck. And also geologist Ray Wells, who was also on my postdoc committee. And he is a wealth of knowledge and kept me in line. All right. So as Carol mentioned, I'm going to talk about Siletzia today. So when we talk about 50 million years ago, that's Siletzia in Western Washington. Okay. So first of all, what is Siletzia? It's also called the Coast Range Volcanic Province. This is a simplified geologic map of Western Oregon and Washington. Formed. I don't know if you guys got the lowdown on the kind of what the hypotheses were back in the 80s, but there were two kind of major ones several decades ago. The first is that it was a group of seamounts that was erupted underneath the Pacific Ocean that got rafted into a subduction zone on the west coast of North America and smashed into the continent. So that is the model that I have in my title. What happens when Iceland crashes into North America? So you already know what I'm going for here, right? But the other option that was developed extensively in the 80s and 90s was that there may have been a period of extension and that all of these basalts were actually erupted in place on the margin of North America. And there are a lot of studies that have mapped extensive areas where there were Eocene 50 million year old basins that collected a lot of sediment and were mapped extensively. And in looking at those basins, people thought, hey, maybe we actually had an extensive period, we had these basins developing, and the volcanics is a natural result of that. And it's kind of one or the other. People weren't sure, what it was. And so I kind of want to use that as a starting point and say, hey, how can we tell the difference between these two different ideas? Can we actually understand which story is correct? So this one is the Iceland crashing into North America. And this one over here, I think the modern idea would be a far triangle in Africa where you're rifting apart the edge of a continent, and you're filling in with volcanics, and there's eruptions, and there's also basins developing. So how can we tell the difference? Well, the two questions I want to think about in terms of trying to answer how do we tell the difference. First of all, where is the boundary between Siletzia and North America? Like where is this zone or this zone here in this model? And what does it look like? Maybe that could tell us the difference between the two. The other one is the structure of Siletzia itself, like inside Siletzia. Is it consistent with one or other of these stories? And can that help us understand, which one is correct? All right, so let's go look at the boundary. Oh, shoot. Look at this. Here's the boundary-ish between Siletzia and North America, and it's covered with quaternary volcanic rocks, Cascades volcanics, there's sediments, there's glacial deposits, there's trees. The boundary is largely covered up by all of these components. And so it's a very difficult problem to say, hey, let's just go look at this boundary, look at the rocks and see what they tell us about how Siletzia formed and became a part of North America. So maybe we need to use geophysics. And I'm showing on the left here a picture of the gravitational anomaly of that same region of coast ranges. So there's the coast ranges there, and this is the gravity map of Western Washington and Oregon. And I'm going to talk more about what gravity is and what it tells us in a minute. But you can kind of think that, all right, if a rock has more mass, if it's really dense, it's going to make gravity higher in that spot when you try to measure it. And has anybody dropped a block of basalt on their foot? Yeah, it's heavy stuff, right? Heavier than a lot of rocks. And it actually creates this gravity high that you can see is correlated where we have the mapped outcrops of Siletzia. And to the east, it drops off and it's a little less high, indicating the rocks are less dense. So using this style of geophysics might be able to tell us something about the structures and what it looks like underneath the surface. All right, so, let me go back here. So the study that I did, I'm going to dive into the area where I did my work, which is right here in the Puget Lowland. So this box kind of shows where all my work has been done. And there's not a lot of other work that's been done on these questions going south, though you'll notice that I kind of glossed over something down here. Notice that the coast ranges come up right up against this green stuff, which is older rocks in the Klamath Mountains. And I'm going to come back around to that area at the end. So just stay tuned. There is a place where the boundary is exposed, and I'm going to show you the results there. So we're going to get a view of the north here, and then I'll show you the south at the end. Okay, so bear with me. There's a lot going on this slide and in this map. But this is the area that I just outlined on the previous image. So here's the Olympic Mountains. Here's the Cascade Mountains. And all of these blue lines are the waterways of the Puget Lowland. So you might see some familiar shapes like Lake Washington here. Seattle's right about there. There's Bainbridge Island and Kingston's up here. And I think we're just off the map up over here. What else I'm showing here on this map is all the colors are different rocks of the basement. And when I say basement, I'm talking about all the really old rocks that are supporting all the younger rocks on the surface, kind of the fundamental bottom of the stack of the geology of the region. And in the Puget Lowland, in the Olympic Mountains, Siletzia forms the basement, and here it's called the Crescent Formation. Over in the Cascades, the basement is made up of another kind of rock called the Western Melange Belt. So we talked about what Siletzia is made up of. The Western Melange Belt is a little bit different. There's some igneous rocks, there's gabbros, but it's mostly something called metasedimentary. So it's a sedimentary rock that's been buried and squeezed and metamorphosed. It's a little bit more dense than a sedimentary rock. And that makes up all of these different outcrops here along the foothills of the Cascades. All the white area is all the area where we don't know what the basement is. It's not exposed. And so if we're thinking about where is the boundary between these two fundamental pieces of rock and what does it look like, we're going to have to look somewhere in the Puget lowland. So we need to focus in on the lowland. Let's see. Okay, so that's what the basement is. The last thing that's on here are a bunch of faults. Carol mentioned that my main job at the Washington Geological Survey is studying active faults that might create earthquakes and characterizing them so that we understand how hazardous they are for people. And I'm showing you a bunch of the different mapped active faults in the Puget lowland. I think, who here is familiar with the Seattle Fault? Raise your hand. Yeah, quite a few. Yeah, this is the famous one, right? So that's this one right here. Comes right across south of Seattle, kind of through West Seattle. But there's other faults that are active in the area. This is the Southern Moby Island Fault. This is the White River Fault. There are actually many of them. And I'm going to be coming back to them also at the very end of the talk. So I want you to kind of absorb that there's faults here, and I'm going to talk about them again. But we're really going to dwell on the basement for a while here. Okay, so let's talk about, I was mentioning that the dense rocks can make a gravity high, and I'm going to start diving into that. But we have actually a really cool relationship here between the Siletzia Crescent Formation and the Western Melange Belt. The Crescent Formation is very dense, but it's also very magnetic. It has a lot of the mineral magnetite in it. And you guys are familiar with magnetite. If you're a hiker, magnetite is what you have in the needle of your compass that helps it point to north. So you can actually sense, using like something like a magnet, whether there's magnetite in a rock. Turns out the Western Melange Belt is less dense and not very magnetic. So not only do we have a contrast in rock density, and we can use gravity to understand the boundary, there's also this contrast in magnetism that we can use to understand the boundary. So now I want to take a little side trip into gravity and magnetic data and explain to you how we use it, and then come back to this question about how do we use this to find the boundary. Okay, so this is actually a quarry down in near Doty, Washington, west of Chehalis, and it's a beautiful, beautiful exposure of sedimentary rocks on the right that are tilted, and then there's basalts on the left, and those are Columbia River basalts that are actually in the Doty Hills. And this kind of boundary, a very steep boundary between the two, whether you take a set of rocks and turn them up on end and you have two rocks side by side, or if you have a fault that faults them and juxtaposes two different rocks side by side, you can use gravity and magnetics to tell what kind of rock is where and what that boundary looks like. And so I'm showing that on the left here. So if you have a high density rock and a low density rock, so again, like igneous rocks are dense, basalt, hey, crescent formation, or granite is also quite dense. Less dense would be sedimentary rocks or the metasedimentary rocks of Western Melange Belt. And you'll notice that if we measure gravity, let's say we walked across the surface here measuring the pull of gravity, you have a higher pull when you're right above the high density rocks and lower pull when you're right over the low density rocks. Now, the transition between the two, let's say there's a fault that we're trying to map or understand. As we transition between those two regions, you get this kind of S-shaped curve in the gravity values. And right where you have the steepest kind of slope on that curve, we call that a gravity gradient. So you're going from high to low, and it's the point at which it's changing the fastest as you move across the surface. And so as a geologist trying to understand structures in the subsurface, we're looking for these gradients all the time. So I'm going to start saying gravity gradient and magnetic gradient, and that's what I mean. It's the place the fault is likely to be. All right, cool. And turns out magnetic relationships are similar. Not only is there a gradient between areas of high and low magnetic rocks, there's also a relationship that igneous rocks like basalt or granite tend to be more magnetic than sedimentary rocks. And so you end up having these two kinds of data kind of telling us the same parts of the story. And so when you put them together, you have more power of data to put towards your interpretation. All right, so I have asserted that the Siletzia is more magnetic and more dense, and Western Melange Belt is less dense and less magnetic. How do I know that? Well, my collaborator, Joe Dragovich, dragged me around to hundreds of outcrops, and he knew where they all were, so he is an extremely important person in this work. And we measured the density of those rocks in those places and their magnetism. So notice the density for Siletzia is 2860 kilograms per meter cubed, and Western Melange Belt is 2730 kilograms per meter cubed. It doesn't seem like a big difference, but it's a large enough difference that with our modern instrumentation, we can actually measure gravitational changes that show us that difference. Great. So magnetism, the rocks in the Crescent Formation, Siletzia, are 14 times 10 to the third SI. That's a unit. I'm not going to bother explaining that. And you can notice that the magnetism of the rocks in the Western Melange Belt are 3. So there's almost, 5 times difference between the two in terms of the magnetism as well. And so this is just done in a lab. We take samples, we put them in the lab and measure them. All right. So hopefully that convinces you that we know what the differences are. All right. So remember, when we're talking about Siletzia, we're talking about this rock, and what Western Melange Belt is this rock, North America. Siletzia is this rock, and Western Melange Belt is North America. So less magnetic, less dense, more magnetic, more dense. All right. I'm trying to remember what my next slide is. Okay, great. So now that we have set up that we should be able to see the boundary based on these measurements of gravity and magnetism, how do we do that? Well, I want to show you a couple slides that show you what we do. So on the left here, I'm showing you pictures from the field of how we measure gravity. This is a gravimeter here. Here's another style. We run around, drive around, hike around, and we put this box on the surface, and we measure gravity. Point to point to point to point to point. We do a lot of driving on forest roads. It's pretty fun. Magnetics is a little easier to get. You can actually put a magnetometer in an airplane, as shown here. This is just like a low-flying kind of crop duster style airplane, and the magnetometer is in something called a stinger, which is out the back, so the magnetometer is way out here to be away from the engine, and so you don't have any magnetic fields from the engine affecting the data. You can also walk around with one of these magnetometers on your back, and we do that sometimes too, but airplanes way more efficient. People are actually starting to do a lot of drone magnetometry too now, and that's becoming a big thing. I'm going to show you what we do. We basically take, I'm going to use the gravity as the illustration. We take this one measurement we take at this one point, and we plot it up on a map. So all these little dots in here, those are all places where, in this example map, where we measured gravity. And then we use a computer to try to connect between the two and infer what it does in between. So it makes a map of where the highs and the lows are. And so in all of my maps, I'm going to be showing high gravity and high magnetism as these warm kind of pink colors, and low gravity and low magnetism as these kind of cool colors here. All right, so just a quick fun thing on units. So the units that we use for gravity are called milligals. If you guys remember back to your high school physics, if you took physics in high school physics, you learned that the value of gravity is 9.8 meters per second squared. Well, with our instruments, we actually can measure, what is that? 8 decimal places out in that number with enough precision to matter. And so the units that we use are actually in kind of the thousandths place out here. And so we're measuring really, really, really tiny changes in gravity. And so these instruments are extremely sensitive. If you got on a scale up here and down here, would you weigh different? No. Too bad. All right. So let's come back around to the Puget Lowland. All right, we've got this map. I'm showing you kind of what we know of the geology. And next, I'm going to show you what the gravity looks like. There it is. So same area, but in gravity. And I'm going to point out a few things. You'll notice that the Olympics were over here. Notice there's a big arc of really high values, gravity values, along the edge of the Olympics. The center of the Olympics is low. There's a big blue bullseye over Seattle. And as we get in the Cascades, we kind of have these moderate values. They're not very high at all. So here's a couple of different features that people talk about and have viewed from other kinds of data. There's this area where we have kind of a slight high is called the Kingston Arch. This bullseye is called the Seattle Basin, and it's a pretty young feature. Notice that there's a place right here where we transition from high to low. That's where the Seattle Fault is. And so it's a big gradient. So the fault makes the gradient. And down here we have the Seattle uplift, which is a high. And I think I actually split these out. Oh yeah, so one of the things I want to point out is that this low up in the Olympics, if you actually go and look at the rocks, we can actually see the rocks there. It's a big pile of sedimentary rocks and metasedimentary rocks that have been accreted via the subduction zone. And so that's what's making this low. We can actually see it. So we can say, oh, well, if this is a bunch of accreted metasedimentary rocks, anywhere that's green on this map might be a bunch more sedimentary rocks too, like over here, or maybe in the Seattle Basin. And so this map is already starting to tell us about what's in the subsurface that you can't see. Let's see. Yep, I already pointed out the Seattle Fault gradient. And I'm drawing a line here because if we're trying to think about, all right, where's the boundary then between Siletzia, which is these rocks exposed here, and Western Melange Belt, which is over here, there's kind of a place where we go from mainly pinks over here to more like greens and yellows over here. You guys with me? It's kind of this transition there, right? And so if we were to draw a line on this map just by eye, we might draw it right through here. So is that where the boundary is? Maybe. All right, so here is the magnetic map. So again, the magnetism can show us similar things. It's a little bit more complicated. Again, you've got this nice, do you see this boundary here, this gradient? That's the Seattle Fault again. Great, it shines out really nicely. But it's a little bit more complicated up in the Olympics. The area with low magnetism is a little bigger than for the gravity, so that's kind of confusing. And, oh, here, I said this was a Seattle uplift. It's an area where the rocks of Siletzia have maybe been brought up closer to the surface. There's some weird stripes going across there. And what's this big high out here? It's a little bit more complicated. So in order to use the magnetics to understand the basement rocks, which is what we're trying to do, I applied a filter to this data. So this is the original data I was just showing you. And on the right is the filtered data. And let me just explain what I'm doing here. So I applied something called a long wavelength filter to this data. Imagine you're looking at a transect through this data, like if you pulled out kind of just a line of data, and we're looking at the ups and downs in the magnetic data. It actually looks something like what's on the bottom here. See that guy here? It's pretty complicated. There's kind of long highs and lows, but then there's little smaller highs and lows up on top of that. And mathematically, you can actually take those two components, kind of like the short wavelength and the long wavelength data, and pull them apart from each other. And so that's what we're doing here. So you'll notice that in this example, and of course this is running out of battery, this long wavelength here added with the shorter wavelength information here creates this total here. And so what we're doing here is removing the shorter wavelength stuff in order to isolate the longer wavelength one. And the reason that I wanted to do this is because the deeper a rock is down below the surface, the longer wavelength anomaly it makes in the gravity and magnetic data. So if we want to see what's happening deeper, we need to remove all the little ups and downs from the near surface stuff out of the data. And so you'll notice when we do that here, we go from this plot to this plot. And you can start to really see the difference between the areas where we have Siletzia and the areas where we don't. And so this is the data that we use to go on with our analysis. All right, so there's that line again. Separates high magnetism from low magnetism. Great. Looks fantastic. So maybe that's where the boundary is. Do you notice anything weird in the center? It kind of goes across this area here, right? And so it was really unclear initially, does the boundary actually come and jump over here? That seems more logical based on the data, right? Or maybe it comes out here. Notice that there's this kind of area between the blue and the green where it seems like there's a boundary that comes out here, maybe connects down that way. It's a little bit unclear. And the reason is that the Seattle Basin is on top of all of this stuff. It's a big pile of sedimentary rock that is basically obscuring what's down below. And so that makes it very difficult to understand where does it go across that section. So in order to understand that better and to understand what might be in the subsurface, we did another technique to the data, and that's modeling. So what we did is we pulled 3 different profiles. So the kind of the wiggles in the data, we kind of just pulled it out of the map data and put it into a modeling code and tried to see if we could figure out what the subsurface looks like to match the data. So I explained to you that process. All right, so the first one I'm going to start with is the Seattle uplift. That's this line here. And I'm going to tell you what's all going on in here. So in the bottom, we have our model. So this is like if you took a knife and sliced through the earth and were able to open it up, that's what you would see going across that line. I also have gravity data and magnetic data in the upper 2 panels. And what this modeling code does is you can assign values to blocks of material in the subsurface, density values and magnetic values, like the rock determinations I was telling you about. And it will predict what this set of blocks, these pieces of rock in the subsurface, would create in terms of a gravity and magnetic anomaly. So that's the lines that you see here. There's the gravity anomaly created by the model I show here. And there's the magnetic prediction. The dots here are my data. Those are the data we went out and collected with the airplane and with the gravimeter. And so what we're trying to do is guess at what is in the subsurface, maybe an educated guess because we're geologists, and then see if it matches the data to see if it's correct. And so that is how we kind of test it out. Well, we know where the boundary is, but what does it look like? What are the pieces and how are they interacting to create what we see in the data? And the red arrow shows here the boundary between Western Melange Belt and the crescent, and it is actually right there. Yay, it works. But there's other things going on in here, right? Not just a boundary between 2 different basement rocks. In fact, you'll notice that within Siletzia here, there are zones where we have really high magnetism and zones where we have really low magnetism. And the gravity, though, however, is all equally high. So there's some parts of Siletzia that seem to be not that magnetic. And this modeling process we use to understand what do those shapes look like? What could they look like? And this is what we see. We see that in the Olympics, we have low magnetism up here, and then where it's exposed here, this is the lower part of the crescent formation. And over here, the upper part of the crescent formation is more magnetic. And one of the things that we did, we went into the Olympics and we did some transects going right through the outcrops of these two sections of the crescent, and we measured the magnetism in these transects going all along a couple of the roads diving into the center of the Olympics. And we did indeed see that there are parts of the lower crescent that are not that magnetic. And so there's just a section of the crescent formation that's not as magnetic. Well, look, there's another piece out here in the center of the Puget Lowland that's not that magnetic. There seems to be these repeated blocks where you have high, low, high, low. And so what is going on with that? Let's see if the Kingston Arch works the same way. I'm going to skip the Seattle Basin because it's complicated, but it's in the paper if you want to look at it. All right. Oh, hey, here's another detail. Do you notice there's this weird thing here? The boundary between the Western Melange Belt and the Crescent Formation here actually dips to the west. All right. And I did a bunch of experimentation with basic models to see if the shape of the anomalies could actually show us that, and they can. Here's the profile from that last model here, shown here. And you'll notice that depending on which way, what the orientation of this boundary is, whether it's straight up and down vertical or if it dips at some sort of angle, we get different shapes to the gravity curve. And in particular, this kind of orientation gives us this kind of convex up shape and a little like kink at the bottom. And that's really what we are seeing in the gravity curve for the Seattle uplift. Cool. So let's look at Kingston Arch next. Okay, so again, same kind of setup. You'll notice that we have even more blocks of this low magnetism crescent. And then you'll notice that the gravity curve is kind of like concave up a little bit more here, indicating that the boundary actually dips the opposite way across Kingston. So there's major boundary between fundamental rocks, and it's dipping one way in the north and the opposite way in the south. Whoa, that's crazy. In addition, you'll notice that we have the same problem here. We've got high gravity where we have Siletzia in the subsurface, but the magnetism goes up and down, right? And that's why we have to put more of these blocks of low magnetism material inside of Siletzia. So we're starting to get an idea about what the boundary looks like, where it is, and also kind of what Siletzia looks like itself, right? And if you remember the first few questions I posed, we're kind of getting into that. All right, so based on the modeling, the boundary is actually out here. And what is happening here is the influence of the Seattle Basin sediments. So this is the boundary. We're drawing it on a map. It goes through Lake Washington. I can say definitively. Yay, we found it. So that's exciting. So where is the boundary? Well, we found it. It's underneath Lake Washington. And what does it look like? Well, it dips. It's pretty sharp. It's not like there's a gradation, like you go from Western Melange Belt and there's a sharp line, and then you have Siletzia. And it dips one way in the north and the other way in the south. Great. Now, what about the structure of Siletzia? What about that structure, those weird blocks of low magnetism material we saw in the Crescent Formation? Well, let's put these two blocks side by side. So the questions I have is, why does the boundary switch dip direction? How do we account for these weird blocks of material? There's a few possibilities. I'm not going to discuss them all, but one of them kind of accounts for almost everything. So what if all the magnetic lows, these pinks, are just the base of the crescent, this area in the Olympics where you have the low magnetic crescent formation. If we go with that hypothesis, then maybe what we've got here is blocks of crescent that are basically laid against each other, repeating in a stack. And in between each of these blocks is a fault. And so those are the faults that I've drawn on here. And this westward dip might indicate that this material, Siletzia, was shoved up and over the edge of North America. Interesting. So if we think about what our models say about kind of classical structural geology and back out and think about what would this have looked like 50 million years ago, of course, right now, all of the material that would have been up in the air has been eroded. So we've kind of cut off the material. And all of the stuff that's down below probably got subducted if we're talking about accretion or stacking rocks on top of each other. But this is just me drawing from my imagination what it would have looked like. So here's the Kingston Arch. You've shoved a bunch of slices of the crescent formation, Siletzia, up underneath each other here, and it got shoved down underneath the edge of Western North America. But in the south, we have actually much thicker pieces of that magnetic upper part that got stacked together and got shoved up and over the edge of Western North America. So it's a very different kind of stories going from the north to the south. So if we think about, well, where is this happening in the world today? Does this have an analog? And one place where that's happening is modern-day Taiwan. So the edge of the Asian continent is being shoved into the subduction zone there, and you're creating a huge mountain range, and that creates the island of Taiwan. And you'll notice this cross-section of Taiwan, we have a bunch of stacked material. As the material is being shoved together, it's stacking up on top of itself to create what we call a fold and thrust belt. And so this is kind of maybe a place where it is currently happening. In addition, I think I told you I was going to loop back around to the southern part of Siletzia. Well, here we are down in Oregon. So there's that zone that I kind of skipped over at the beginning. My postdoc committee member, Ray Wells, mapped structures in that area that are actually exposed at the surface near Roseburg, the Klamath Range. And this is the picture that he surmised from his mapping of the surface. Basically take rocks of the same age that I'm mapping here with the geophysic, and you stack them up into a fold and thrust belt. So in southern Oregon, that boundary is exposed and you can see it. And what we're seeing from the geophysics in the northern boundary looks very similar. We just can't see it at the surface. So now we're kind of seeing very similar stories from the north and the south. They're kind of telling the same kind of idea. You squished Siletzia onto North America and you stacked the material up. It broke and stacked up into this series of uplifts and mountain ranges. And the surface would have looked like back then, like Taiwan. All right. So I was like, yeah, this is a cool story. I think I'm going to publish this in Tectonics. Sounds great. We're like, let's just take this idea and go as far as possible with it. The very last part of the story is saying, hey, we've got these models. We have this idea of what the subsurface looks like. What if we just apply that to the whole Puget Sound and create a fault map of where the faults would have been in this fold and thrust belt 50 million years ago? So what I did here was a little bit more math. I mentioned these gradients before, right? That's the location where you'd have a fault or a steeply dipping boundary. And I used a mathematical computation to try to identify in the map view data, so this is the magnetic data, all the places where we have a really sharp gradient like that, all right? And all the blue dots are the places that we see that. And you can see, number one, there's the Siletzia boundary mapped out, shows up, nice straight line, yay. We can also see Seattle Fault here, but we also see a bunch of other lines going through here. So I took these and I just said, okay, let me just digitize these into sections that I think make sense. So this is what it would look like. So what I'm showing here is there's the boundary with Siletzia in the north. Again, it's dipping to the east. In the south, it's dipping to the west. And you notice that the lines that are bounding these different thrust slices and blocks that got squeezed together have a distinctive orientation in the north that's more north-south. And in the south, there's a different orientation. It's northeast, southwest. It's almost like these faults have how it developed. There's a different orientation, and there's like a very, very sudden change between those orientations right in here. So there's the major trends that I saw with my eyes. So how do you do that in a fold and thrust belt? You have to have something called a tear fault. So it's a place where you have one set of structures over here and one set over here, and maybe they're different orientations. There has to be a vertical fault that basically disconnects the two sides from each other, a place that allows that transition to happen. All right, so there's going to be basically an east-west fault that would provide that accommodation. Well, where is this east-west fault? It's at the Seattle Fault. So the implication is that the Seattle Fault it's a modern fault. It's created earthquakes that are documented by geologists. It may have started during the creation and accretion of Siletzia 50 million years ago, which is pretty darn cool. Does it give us information about the hazards to the Seattle Fault? Probably not. But I don't know. Maybe someone will think about it in the future. But it's a pretty cool idea that the Seattle Fault actually has this really early old history. And the modern tectonics are just using that to make new things happen. Anyway, I hope you guys are convinced. Yeah? Okay, I got one yes. That's great. I'm not the only one saying this. So how was Siletzia formed? I think it's the oceanic plateau accretion. I think we slammed Iceland into North America is what happened. And there are other people who are hypothesizing the same thing. Ray Wells, with his structural mapping of his whole career, really, came up with a similar idea in 2014. McCrory did a bunch of plate reconstructions, rated to, suggesting that there was a plate or an island chain of islands like Iceland that slammed into the continent. There's this guy, Jet Tepper. You guys know him? Using geochemistry, maybe coming up with a similar idea. So there's a bunch of different data that is feeding into this and kind of helping bolster this idea. In addition, Erin Donahue gave a talk here in 2022, and her paper on this mapping in this area just west of Port Townsend is in press, and I got an advanced copy from her. And here's her map. Look at that. Isn't that beautiful? It's just a ton of work. Here's Port Townsend. But this is really cool. This is her. She was really mapping out the sedimentary rocks and trying to understand the story that the sediments had to tell about what was happening through time. And her picture, a block model showing what she thought was happening during the deposition of the Lyre Formation at the time of the accretion of Siletzia, she thought there were faults here too, and uplifts. And so she envisions isolated mountain ranges kind of out in the Puget Lowland with sediments filling up basins in between. And so if we'd stood on Mount Erie and looked out, maybe that's what we would have seen 50 million years ago. So maybe less of like a big old chunk like Taiwan and more isolated little ranges with sediments filling in between. But the whole Puget Lowland would have been filled with mountain ranges. Cool. All right, so does it answer the second question? Yeah. Iceland accreted to North America. Siletzia. Awesome. So here's a teaser. Remember that long wavelength filter magnetic data I was talking about? The area that I was studying is up here. This is the magnetic data that extends all along western Washington. And in 2016, a major piece was flown and kind of connected up to older surveys. And in 2023, the Southern Cascades was flown. So this is brand new data, and people are just trying to understand it. But if you look at the long wavelength magnetic features, this is the area I was showing you. There's a lot going on, lots of highs and lows. Look at this sucker right there. What is that? What does that mean? And I'm really interested in trying to use this information now in the future to understand, hey, what did Siletzia look like? Like, what was its internal structure? Did it look like Iceland? Can we use Iceland as an analog and think about what the material is down there? And so I have lots of ideas, and that's a whole nother talk. Got to get going on another paper. So anyway, I would like to thank you for your attention. Here's the paper, and look at this huge group of people who contributed to this research. It's not just me and my co-authors, but I had students come get data with me, WGS employees, geologists collaborating. It takes a whole huge group of people to make this work. So thank you so much for your attention, and I'll take questions. Did you guys get it? Give me a thumbs up, sideways. Thumbs up. Oh, good. I see lots of thumbs up. Great. Awesome. You guys have a PhD in geophysics now. Yeah. So the question was, do I have any ideas about why the lower crescent would be less magnetic? And yes, all sorts of ideas. Something I glossed over a little bit is that it could actually be what's called reversed. So it might have been erupted at a time when the Earth's magnetic field was reverse of what it is now. So that could be a reason why it's differently magnetic. But if you look at actually the geochemistry of the rock, looking at the chemical studies that have been done of the lower crescent in the Olympics in particular, it seems there's been a lot of alteration and kind of low temperature alteration that may have actually taken the magnetites that were originally in the rock and changed them to be more hematite, which is less magnetic, or other kinds of less magnetic minerals. It could be that the original chemistry of the rocks that were erupted early and late in the process had less and then more magnetite. There's a number of different reasons why that could be. And I think the important thing is that we were able to do those two transects where we could see the change and then use that.
We know it's real.
Mm-hmm. So we know it's real. Yeah. Great question.
Not too far from Philippines is a quarry called Penny Creek. And rocks there are highly magnetic. That is the relationship what you're talking about.
The question, what was the name of the quarry?
Penny Creek.
So, right. So the question is near Quilcene, Penny Creek quarry has highly magnetic rocks. And does that have anything to do with the story? Yeah, absolutely. That would be part of the upper crescent, I believe. And so that's an example of how the upper part of the crescent is really magnetic. And so really shows up creating those magnetic highs on the map.
And if you haven't been to Penny Creek, it's a beautiful quarry, beautiful fault rim right through the face.
Can we go sometime? I haven't been
We
there.
actually had a field trip go there not too long ago. And
Missed it.
they recycle that field trip in the future.
That'd be great.
Other questions?
So the question is the part of the fold and thrust belt that got eroded, maybe there was some folding and then it got eroded off. Question is, how much uplift might there have been and how much was eroded? It's really not clear. When you go in and try to create a drawing of the fold and thrust belt, as I tried to do, since that stuff has been eroded, we really don't know, if you take one piece of material and shove it up underneath the other, how far that went up before it folded over, right? And really what you do as a structural geologist is you try to fold it over as quick as possible to make the offset as low as possible and be conservative about what you're estimating. So we really don't know. One of the things that is clear from doing those kinds of sketches is that a huge amount of the lower crescent actually isn't preserved within the fold and thrust belt that I imaged. And so there's a suggestion, because it's not there, that parts of the lower crust actually got subducted along with the plate and now has been subducted under North America. It's now somewhere hanging out under eastern Washington or Idaho or something. Yeah, so the question is whether, what does this story have to do with what's going on like out here, 50 million years ago, so kind of after it was accreted. And I think that the story that I have to tell is probably mostly about the accretion process itself. But as I mentioned early in the talk when I was introducing the idea of having a rifted margin as a source of Siletzia, there is a lot of Eocene extension and sedimentation that happened during that time. And so if I'm not misremembering what Jeff wrote in his paper, that maybe that period of time you would have had the extension. So you're doing a lot in an incredibly short period of time. You take this island arc, you smash it into Washington and Oregon, and you create this huge mountain belt as it's smashing, and then you set up a kind of tectonic environment where you're actually extending it. So you like smash it together and then pull it apart. It's like an accordion, zoop, zoop. And then I'll let Jeff talk about what happens after, which is really a lot of what his paper is about. Yeah.
You want me to say something?
Sure.
Okay, so this is not really my work, but the cartoon on the left that's dated 52 million years that shows Siletzia sitting on top of a thread. So I think most popular model of Siletzia is formed where a hotspot like Iceland sat under the thread like Iceland. So that explains part why there's voluminous activity. And a new hotspot is an incredibly productive environment. But that whole system was moving eastward. So once it collided with North America, that pressure rates that shown in dashed lines on the left became inactive. And all the action shifted out of the sea, except for all the action we talked about.
Yeah.
Crushing
it, yeah, exactly. Great. I'm not going to repeat all that.
Repeat it for the film.